Good afternoon. Welcome to today's broadcast on Would You Recommend Drilling a Dry Hole? We have Bob Shoup is our presenter today. Bob is the Chief Engineer for SCA, and he has over 35 years experience in various aspects of geoscience. He has a master's in geology from Oklahoma, and he began his career at Shell in 1980. He's also worked with private oil companies and has done quite a bit of consulting in both the Asia-Pacific region and in the U.S. Gulf of Mexico area. He's an expert in clastics, and he's an active contributor in many ways in the professional community, including having served as the chair of the House of Delegates for APG, past president of DPA, and past secretary editor of the House of Delegates of APG. He's received numerous awards, including DPA's Distinguished Service Award and Honorary Life Membership in the DPA, Division of Professional Affairs. He currently lectures on ethics as well as various geoscience topics and is active in both Southeast Asia and the United States. So today, Bob's going to give a sample of a class that he teaches for SCA on QC techniques for reviewing prospects and acquisitions. This is being offered in Houston, Texas in late May, early June, and you can see the description there. There's still time to register for this class. So, of course, you can attend this public class offered in Houston, or you can schedule an in-house class by contacting us to have it brought to your location. This is part of our webinar series that SCA has been offering this year. Coming up at the end of May, we have Med Kamal on May 31st speaking on determination of in situ reservoir absolute permeability under multi-phase flow conditions using transient well testing. And then June 13th, we have Maggie Delthorpe on opportunity analysis, the sport of matching company objectives with available opportunities. And of course, this is part of the offerings that SCA provides. In addition to training, we also do consulting, direct hire services, projects, and studies. And so I'm going to take a couple of moments to poll our audience today. And so you should see the first polling question of what is your primary discipline. So here's a chance for us to find out what the background is of the people who are attending our audience. Looks like we've got quite a few geoscientists, no surprise, but also a good representation of petroleum engineers. We're still getting the votes. I'm going to give you a couple more seconds to find that voting button. Let us know if you're in petroleum engineering, geoscience, facility engineering, petrophysics, or other. Looks like most of you have voted, so I'll go ahead and share those results. 67% geoscience. So let's go to the second question. How many years of full-time experience do you have in the oil and gas industry? And we're starting to collect results here. Looks like there are quite a few of you who have over 30 years experience, but a scattering in the other areas as well. Still waiting on all of you to find that voting button. We've got most of the votes in now, so I'll go ahead and close it. And let's share those results. Over half of you have more than 30 years experience. Everyone else is somewhat less. Looks like a good group in the 1 to 10 year range. So let me hide that. And I'm going to go back to giving Bob the presenting rights. And I want to remind you that during this presentation today, you'll be muted. So if you want to ask questions of Bob, please pose the questions in the question feature in your dashboard, and we will cover them at the end of the presentation. Bob, it's all yours.
Thank you, Susan. So we're going to look at the topic today of would you recommend drilling a dry hole? Now, most of us would never knowingly recommend drilling a well if we knew that that well was going to result in a dry hole. In fact, doing so would be an ethical violation, and if we have investors with the well, it could be a potential act of fraud. Yet many of us do recommend wells that are all but guaranteed to be dry holes. And most of us do so because we have a belief in our prospect. We believe we've applied all the appropriate methods and techniques to get a good map. And so we believe our, other than the chance of success factors, we believe it'll be a good well. However, that belief is not sufficient to make our recommendations sound or even ethical. Our managers and our investors expect us to have applied the due diligence necessary to ensure that our wells have a reasonable chance of success. Unfortunately, far too often, we fail to apply that necessary due diligence. And the result is that a lot of our wells are drilled as dry holes. Unfortunately, most of those dry holes could have been avoided had we conducted a pre-drill audit of our maps and interpretations. And failing to have conducted a pre-drill audit is not a sound business practice. And because it does result in dry holes and avoidable dry holes, it's probably an unethical business practice. So I know from teaching around the world that most of you at this point are thinking that a pre-drill audit would not have changed your maps and interpretations. They're as good as the data allows you to make. But let's look at that assumption and see if it's correct. So a number of companies have conducted post-mortem reviews of some of their dry holes, and pretty much they line up with the following reasons for why they think their wells were dry. No structural trap accounts for about 18%. Poor reservoir and seal account for about a third each. And then about 13% of the wells come in as non-commercial, and about 2.5% of the wells fail because the well did not reach the objectives. But SCA does a number of post-mortem reviews for companies as well. And our review of clients' maps pre and post-drill suggests that about 50% of the dry holes are the result of drilling a structure that was not properly mapped. And about a third of the wells, just under a third, where the reservoir was either not reservoir quality or the section was wet, and then still about 13% for non-commercial accumulations. To say that in a different way, about half the wells we've drilled are a failure or dry holes because there was some element of the petroleum system that didn't work. But another 50% represent failures of the map. And that means that almost half the dry holes that industry drills were avoidable had we just made a proper map in the first place. So let's go back and test our assumption that all our interpretations and our maps will be good by conducting a pre-mortem review or a pre-drill audit. Now, pre-drill audit is really nothing more than a critical review of the prospect before we approve it for drilling. It's essentially a post-mortem review minus the cost of the dry hole. So we're going to look at this map and this prospect today. So it's a field in the Texas Gulf Coast. The field produces from a number of tertiary reservoirs, and our development team has proposed drilling 2 additional development wells here and here to accelerate production of the 14,000 foot sand. If I look at the depth structure map for the 14,000 foot sand, you can see that it varies in depth from about 13,500 feet in this fault block to 14,600 feet in this fault block here. The 14,000 foot sand produces from 3 fault blocks. We have these 2 fault blocks to the southwest and this fault block more in the center portion of the field. Well 19 did encounter pay in this fault block here, but well 19 was completed in a deeper sand. So this fault block has been proven, but is not producing at the 14,000 foot sand. The field is covered by 3D seismic, so here's the limits of the seismic here. And there are 9 well penetrations in the 14,000 foot sand. 3 of these wells are producing from the 14,000 foot sand, and the other wells produce in deeper sands. There are 2 wells right in here where the 14,000 foot sand was faulted out. We have several wells here where the did not reach the 14,000 foot sand, but produced from shallower sands. So those wells are marked NR, we can use those wells to estimate the top of the 14,000 foot sand. And finally, we have one well over here that's down thrown to the major fault. So well 1 is proposed to drill right here to drain the fault block proven by well 19. Well 2 is proposed to drill this fault block in the center of the field, which is untested. The dry hole costs for each of these wells are just over $5 million. And our development team has come back and said that the chance of success for well number 1 is 99%. In fact, the only reason they didn't give it 100%, it was a company philosophy that you don't have a chance of success of 1. Well number 2 was given a chance of success of 83%, and the risk return on investment for that well was 9.5 to 1. So the question then is, would you approve drilling these low risk and high reward wells? So before we approve these wells, let's take a moment to critically review the map. And the first step of that is to step away from the postage stamp view and think about the geology that we're looking at. So our field is located here in the Texas Gulf Coast, which means that we're looking at growth fault structures. Regional dip in the Texas Gulf Coast is to the south to southeast. But the dip in our field is about 7 degrees and is dipping predominantly to the north. And what that tells us then is that our field is in the front limb of a growth fault rollover structure. So if I look at a seismic profile across the field, we can see that the dip is predominantly to the north-northwest. I can use my understanding of rollover structures to predict what the front limb dip of the fold will be. So here's my rollover fold. So the dip of the front limb here, theta, is related to the dip of the fault above the horizon on a mapping, which we call beta, and the dip of the fault below the horizon on mapping, which we call alpha 1. And then I take alpha 1, subtract beta from that, and I get the term phi, which we can go to a nomogram and then determine the dips. Now I'm going to reverse engineer here. If I've got 7 degrees of dip on the front limb of my fold, the difference then, my A1 or my phi term, will be between 10 and 5 degrees. So if I go to my fault surface map, I can see that the dip above the 14,000 foot horizon on the fault is at 42 degrees, and below the 14,000 foot contour of the fault surface, the dip is 34 degrees, which gives me a difference between my 5 and 10 degrees. Unfortunately, the team did not construct a fault surface map. This is the fault surface map constructed during the post-mortem. Now, since no fault surface maps were constructed, we now have to be concerned that the proper amount of due diligence has not been used in mapping or reviewing this prospect. So given that concern, an audit is required to protect our investors. So our second step now is to conduct an audit of the map. Now the audit consists of 7 steps. The first step is to look at the map and make sure we've honored all of the data and that we've used all of the data. Step 2 in the audit is to look and make sure we've used the appropriate methods and techniques when in our interpretation and in our maps. Step 3, do the contours exhibit contour compatibility? Then we want to make sure that the contours honor vertical separation as they cross faults. We want to make sure that the fault traces are properly positioned. We want to make sure that the map matches the seismic, and we want to make sure the map honors the geology. So let's come back to our map here. And the first question, again, we're going to look at in our audit process is to make sure the map uses and honors all of the data. When I look in some detail here, I've got well 20 that encounters the 14,000 foot sand at a depth of 14,162 feet. Well 22 here encounters the sand at 14,223 feet. But notice that on the map, the contour going through well 20 is the 14,400 foot contour, which means that the fault block here has been mapped with too steep of a dip. And our reserve estimates for that fault block are probably wrong. So coming back to my audit, my map fails step 1. It did not honor all of the data. So now I want to look at the map and make sure that my development team has used all of the appropriate methods and techniques to make sure that I have a valid map and interpretation. Now remember, I have 2 wells that where the 14,000 foot sand was faulted out. The interpreters here did not calculate restored tops. So the map is not using the appropriate methods and techniques. Now, if you're not familiar with restored tops, they represent a position in a well where the horizon would occur if the fault weren't present. So if I look at this well in the middle, it's in the fault gap for the orange horizon. If I project the orange horizon across the fault from the upthrown block to the well, that would be the position in the well where the horizon would occur if the fault weren't present. And I can do the same with the downthrown block. I'll project it across the fault to where it intersects the well, and that would be the position in this well where the downthrown block would occur if the fault weren't present. Now we can calculate restored tops for these 2 wells. It's a fairly simple process, takes about 10 to 15 minutes. Had they calculated the restored tops, we would have seen that the dip in this fault block was wrong and the dip in this fault block was wrong as well. So the contours on both sides of the faults are wrong. So we know the fault blocks then are improperly mapped. So we failed this step of the audit. We have not used the appropriate methods and techniques. Now we want to look at the map and see if it exhibits contour compatibility. Now, contour compatibility pretty much simply means that when I'm crossing a fault, the contours will continue from one side of the fault to the other with pretty much the same strike. I have a fault block here where the contours, as they cross the fault, they intersect at an almost 90 degrees angle. Another fault block where I'm intersecting with a 90-degree angle. This one also with a 90-degree angle. This one about a 45 to 50-degree angle. So those fault blocks were not properly mapped. So I failed this audit step. My map does not have contour compatibility. Now I want to see if the contours honor vertical separation. Vertical separation is simply the amount of offset that I see in my horizon as I go from one side of the fault to the other. Now, one of the ways I can test that is if I can look at fault intersections, the net vertical separation at the fault intersection must sum to 0. So I can look at this example. So I've got a fault intersection here. And if I go from the upthrown block to this block, the difference in contours is 400 feet. And I'm going to use the convention that when my offset of the fault is in a clockwise direction, I will make the vertical separation positive. So I get a positive or plus 400 feet there. If I look at this position on the map, I'm going from 7,300 feet to 7,550. So 150 feet of change in vertical separation. This fault is now offsetting my horizon in a counterclockwise direction. So I'm going to make that minus 150. And I'm going to look at these contours. That gives me a minus 250. The change then, or the net vertical separation, is 0. So if I come back to my map and I look at the vertical separations at this intersection, it's minus 300 feet. So that fault intersection is incorrect. If I look over at this fault intersection, it's plus 125. And if I look at this intersection right there, it's minus 100. So my fault intersections, at least for those 3 faults, are not correct, which means that we have not properly mapped the fault traces, or we're not honoring vertical separation. Also, if I look at this fault right here, key fault separating this producing block from this prospective block, my offset right here is 50 feet, and it's offset from north to south. If I come over to this part of the map right here, I've got 0 feet of offset. This is the 14,100 foot contour in the downthrown block. There's the 14,000 foot or 100 foot contour in the upthrown block. And when I get over here and look at the offset, it's minus 50 feet, which means it's actually 50 feet down to the north. So I'm down to the south, no offset, down to the north. We call those kind of faults screw faults because it's screwing through the section. And because this is an extensional setting, it's also a 3-dimensionally impossible interpretation. So I've now failed at step 4 of my audit process. Now we're going to look to see if the fault traces are in their proper position. Now the fault traces for intersecting faults will exhibit a specific pattern if they were correctly mapped. And here's what that pattern looks like. So what I see on this map, the contours shown here in red are the fault surface contours for my through-going fault or fault A. The blue contours are the fault surface contours for the blue fault or fault A1. I can see that this fault is dipping to the south. My A1 fault is dipping to the south and east. Where the contours of fault A1 intersect contours of the same value on the through-going fault or fault A, they terminate. And they do so along what we call the line of bifurcation. So now the fault traces are shown here. They are integrated with the horizon map and the fault surface map. So the traces for this map are in their correct position. What I want to see looking at the fault pattern then is where these faults intersect, these two intersection points occur on that line of bifurcation. And I will also see that the width of the fault gap changes as I go from this side of the fault to this side of the line of bifurcation. So if I don't see those intersection points lining up, and if I don't see a change in the width of the fault gap, then I know that my fault traces are not in their proper position. So if I come back and look at this map again, every one of these fault intersections shown on the map are not in their, do not display the correct pattern, and that means that the fault traces are not properly mapped. So none of the fault traces here are correct. I can further show that using a concept called implied strike. I'm going to use the contours of the map to determine what the fault strike would be. So if I look at a structure again, so the contour values in this fault block, here's the contour of the same value in the downthrown fault block. The fault surface contour has to be the same as these two contours here. So the connecting contours have to have the same value in the horizon contours. So if I start connecting then all of my upthrown and downthrown contours, and if the map is properly constructed, I will reconstruct then a fault surface map that looks geologically reasonable. When I come in and look at this map and connect upthrown and downthrown contours, I get a kind of north to south trend, then a northwest to southeast trend, and these are not lining up and looking like they're a reasonable fault surface map. Same is true with this fault that separates my well 42 and my well proposed well. So I know from looking at the implied strike of these faults that the faults were not properly mapped and they were not properly integrated with the horizon. So my fault traces are not properly positioned, which means that I failed this step of the audit as well. Now I want to see if the map matches the seismic. If I look at the map here, I've got this fault block here that dips from north to south, where all of my other fault blocks dip from south to north. So let's go back and look at the seismic and see if we see that south dip. So we're looking at this fault block here. When I look at this fault block, I can see that all of my dip is from the southeast to the northwest. No south dip is observed. So the map, at least for that fault block, does not match the seismic. The last step then is to ask or to look at the map and see if it actually honors the geology. Now I know I'm looking at a front limb of a rollover structure. All of my dip should be to the north, but one of my fault blocks is showing south dip, so it does not fit the geology. So I'm going to ask the question in a slightly different way. Does the interpretation honor the reservoir engineering data? Because this is a producing field. Now, it's a depletion drive reservoir, and my reservoir engineers tell me that well 19 here is in pressure communication with well 42. And because this is a depletion drive reservoir, this fault block is partially depleted, which means my well number 1 is almost certainly going to be a non-commercial discovery or a dry hole. So this fault block is at risk. If I look at this fault block, and I talk to my reservoir engineers here, they tell me that well 18 here has produced 150% of the reserves as defined by this map. That's impossible. So my map doesn't honor the geology, nor does it honor the reservoir engineering data. In other words, this map failed every step of the pre-drill audit process. And that just about guarantees that the 2 wells are going to be dry holes, or at least non-commercial or depleted reservoirs. Now, the interpreters who proposed those wells generated their map out of the workstation, and they failed to think about the geology. And they didn't use all of the appropriate methods and techniques that they needed to make a valid map and interpretation. They were simply workstation jockeys. They pushed the buttons to get out of the workstation a map. Now, the managers who approved those wells also failed to apply the appropriate amount of due diligence. And their failure to do so cost their company and their investors just over $10 million. Now, that $10 million loss was easily avoidable. Again, just having run through this 15-minute audit process, we saw that the map was not valid and would lead to dry holes. So by not doing the appropriate amount of due diligence and costing their company and their investment group $10 million, I would also go so far as to say that their actions were unethical. So what would have happened if we had applied the proper methods and techniques, or if the managers had applied the necessary amount of due diligence? They would have generated a map that looked like this. So we can see that here's this, what was the blue fault on the pre-drill. So I've got a fault block here. I've got several fault blocks here, plus some faults up here on this fairly large fault. Here's the reserve distribution then. So I've got this producing fault block, and this block, which you can see now is very different from the original map. In addition, I've got 3 prospective fault blocks for this field. I've got one upthrown to this fault here, got another upthrown block here. Keep in mind that that dry hole was completed or didn't reach this objective. So the estimated top of 13,420 for the map is projected from the TD of the well to this horizon. And then I have a third location right here. So let's look at the 2 maps side by side. If I look at the incorrect map, notice that the fault pattern in here is completely wrong. We were suspicious of that when we did our audit, and notice that the fault traces were not properly mapped. So here's the correct map. So in this case, the proper mapping methods and techniques were not used. We did not apply the due diligence. Both of the wells were drilled with the result that they were dry holes and a loss of $10 million to our company and our manager and our investment team. Comparing that to the correct map, this map was constructed now using the proper mapping methods, and due diligence was applied in reviewing the final map. And we now have 3 prospective blocks, and we would not drill 2 dry holes. We also get a more accurate assessment of the reserves, and we have, again, 3 untested opportunities that warrant drilling. Looking at the incorrect map, the company here did not get a proper reserve estimate. If they end up doing a reserve write-down, that could expose them to prosecution under Sarbanes-Oxley. So most of us, again, would never knowingly recommend drilling a well if we knew that well would be a dry hole. But if we're not using the correct mapping methods, or if we're failing to apply the proper due diligence before we drill the well, we often end up doing just that. So we have a professional and ethical duty to know the mapping methods and techniques that we're going to use to make valid maps and interpretations. And we have a professional and ethical responsibility to apply the amount of due diligence in reviewing those maps to make sure that they are valid and the interpretations are sound. And the failure of our industry to do that has cost us billions of dollars over time. And that's really unethical, because at least half of those losses, again, are due to the fact that the maps were just not made right in the first place. So one of the things you should consider doing if you don't have the in-house expertise to do a pre-drill audit is have SCA come in and do a peer review with you. We can bring in a team that has global experience and the appropriate geological expertise. And it also gives you an outside perspective. So our team will come in without bias and we have no emotional investment in the prospect or the proposed wells. The typical format then for an SCA peer review is to look at review the play and or the prospect with the team, discuss the geology and the interpretation. Then we'll do the audit of the map to make sure that the map is properly portraying the subsurface structure. And then we usually do a Delphi review of the risks so that you have an appropriate chance of success for your volume estimates. Now, many of the methods and techniques that you need to make an accurate interpretation and map in the first place are covered in our signature class, Applied Subsurface Geological Mapping. And if you've not had that class, I recommend that. I know listening to the webinar today, we have a lot of experienced people, and we've often had people coming into this class with 20, 25 years experience thinking, well, they pretty much will know everything. And then when they leave the class, they pretty much all to a person say, I wish I had this class earlier in my career, because there's a lot of things we didn't know. If you're in a position where you're reviewing maps that were generated by somebody else, whether it's in a data room or in your office looking at the products of one of your teams, we have the class called Quality Control Techniques for Reviewing Prospects and Acquisitions. And it teaches you all of the methods that you need to run these pre-drill audits. So if you haven't gone to our website yet, I recommend you do. A full list of our training courses is on the website, as well as some discussion of the 10 habits, a number of which are covered in this talk as well. So that's our talk for today. And I guess I will turn it back over to Susan, who will monitor any questions coming in. Thank you.
Susan, we can't hear you. Still nothing, Susan.
All right. You on, Susan?
Attendee is self-muted, so. If you guys will just hold on just a few minutes, we will get this taken care of, and Susan will get to your questions. Again, if you'll just hold on just a couple of minutes. Not sure why we're not getting Susan's audio up and running yet. I believe she's relogging in. So, okay, yeah. I am getting some questions. People that are not hearing the audio, yes, we understand. We are working on that. So just hold on just a second. We are working on it.
This is Susan.
Yay, there she is. Okay.
Okay, sorry about that technical issue. I want to remind our audience that you can pose questions today using the question feature on GoToWebinar. You will be anonymous, but we welcome your questions. And after today's webinar, you will receive a link to a recording of the webinar. And we will also provide, along with that link, an evaluation form for the webinar and a link to registration details for Bob's classes, including the class that relates to this topic, QC techniques for reviewing prospects and acquisitions, that's being offered in a public class in Houston, May 30th through July 1st. And as we're starting to see some questions come in, Bob, you mentioned early in the webinar that about half the failures that you see in reviewing post-mortems of drilling opportunities are related to maps, and about half are due to the petroleum system. Can you talk a little bit more about that?
Sure. So let me go back up one slide here. So in our post-mortem reviews, we found that just doing the type of audit process we did with this map, that the structure was not there as it was portrayed on the map. And with enough difference that, again, when you drilled the prospect, there really wasn't a trap there at all. So about half of the wells then are drilled with a failure in the map. And so again, the structure, just like our example here, the structure looked one way on the map and was actually not as portrayed in the subsurface, which means that the other 50% of our failures are elements of the petroleum system that we did not, that didn't come together. So it might have been lack of charge or pathway or reservoir. So did that fully address the question that you had?
I believe so.
Okay.
So the next question is related to unconventional reservoirs. How would you apply these QC techniques when your reservoir is more stratigraphic rather than structural?
That's a tougher question, because the audit process is designed to review the maps. With a strat trap, though, you're going to have the top of the reservoir, and you're going to also have the base of the reservoir, and either coming together or some element of the porosity or permeability will pinch out. So you can still apply the audit method. You're just not going to have to worry about faults or contour compatibility as you cross faults. But you still want to make sure that the top of that reservoir sequence and the base of the reservoir sequence are properly mapped. A little bit on that, oftentimes what we see is that the process of gridding will move your picks around so that the map doesn't no longer honors all of the data. So just fixing that can go a long way. And also make sure that when you contour the map in the machine, that you're using the appropriate contouring algorithm, because we can get very different looking maps depending on the algorithm we use.
So the next question, the information you conveyed today was done in less than an hour. How much time does it take to actually complete one of these audits, to do the analysis that you showed us today?
They take about 45 minutes to an hour, depending on the complexity of the map. I mean, the time to discuss our map today is not a whole lot different from the time it takes to actually do the audit. So if we're looking at, so you look at each point of well control, and if they don't honor the contours, that doesn't take long. Looking at the fault traces takes a little more time, but looking at making sure that they use restored tops or looking at the offsets along faults does not really take a lot of time. I think the SCA review of this map after the dry holes were drilled took about an hour to find some of the problems. The discussion of those problems took the better part of an afternoon. We've had one map we did a post-mortem review on. It took us 5 minutes to show that the well would have been a dry hole. So they're not a long process. It's just a process that most companies don't employ.
So you talked a little bit about incorporating reservoir engineering data into the process. How would you include pressure data and geochem data?
It's the same process, and I mean a lot of maps, and that was certainly the case with this map. The interpreters here never went and talked to the reservoir engineers. Had they talked to the reservoir engineers and the reservoir engineer said, look, that well 19 is in pressure communication with well 42, you knew right away that this well here was going to be in trouble. But there's a lot of companies where the reservoir engineers work on a different floor, a few where they work in a different building, and so the conversations that you need to talk to the reservoir engineers often don't happen. When I'm correlating wells, if I've got a pressure difference between one well and the other, I have to understand that pressure difference. And maybe it's miscorrelation, maybe there's a barrier between the two wells, or I'm indicating that I might be in a hydrocarbon column. But I have to understand that. The geochem is generally not an important part for auditing a map. I mean, it's a major part of the petroleum system in that it defines what the source rock is. If I have made fault surface maps, I can look at the migration pathways. So that's more of an appropriate method for looking at structure maps than incorporating the geochem data.
So how is the approach for QCing maps different if it's an in-house generated prospect versus an acquisition or a data room type prospect?
The audit process is pretty much the same, right? So I've got a map, and the audit process is designed to make sure that the map is valid and it portrays the subsurface properly. So in terms of whether I'm reviewing a map from someone in my company or reviewing a map in a data room, it's the same process. So it's blind as to who made the map.
The next question is, please discuss how they got the dip wrong from the seismic.
That is probably a gridding issue. Could be the contouring algorithm. What gridding does is it takes my irregular distribution of data and it reorganizes it to make it a regular grid. And it will occasionally move points considerably. I've worked prospects where it's changed the sense of offset across a fault from a normal fault to a reverse fault. Or in this case, again, it's just reversed the dip by making grid points here that were deeper than they should have been. In our opinion, it should never, ever have ended up that way. They should have seen that pretty much right away and fixed it. But again, we're often using our workstations automatically. Step 1, pick. Step 2, grid. Step 3, contour. And we don't go back and check. If they had simply taken their seismic profiles and posted on them the horizon as they picked it and the horizon as the machine gridded it, they would have seen instantly that this fault block had been reversed in dip sense.
So can you discuss the differences between incorporating this audit process at the end of the workflow versus doing it throughout the workflow as you go?
Well, we recommend that you use the correct methods and techniques in the first place so that you don't end up with a map like this. That you want to end up with a map that's correct in the first place. Let's go to the comparison here. So if I look at this map here, so what we see is the correct map is just as easy to generate as the incorrect map. So if I'd made the map correct in the first place, then when I go through the audit process, it just validates that this map is fine. And we would never recommend make an incorrect map and then fix it by the audit process. But what typically happens is again, we're generating these maps in workstations. And so after we pick and grid and contour, almost every map, and I'd actually go so far as to say every map as it first comes out of the workstation is incorrect. And it's usually incorrect because of gridding and for algorithm issues. But the software cannot appropriately carry the horizons across faults, and the computers don't know how to handle or generate contours that are compatible. So pretty much every map as it comes out of the workstation needs a little bit of correction and adjustment. And the audit process will make that much faster for you.
So is there anything else?
Self-audit than have your management audit it and tell you your maps are wrong.
Is there anything else you can tell us on how to change your workflow to avoid these problems?
Well, we cover some of that in our new course on mapping with the Petroleum workstation. First thing I recommend is don't auto pick. You may auto pick, but you're going to have to go in and correct your picks. Once you have the picks on your horizons to the point where you like them, then the kind of a crucial step is to decide whether you're going to grid or triangulate. And most people grid, so you have to look at the size of the grid cell relative to your picks. Triangulation works a little bit better in giving you a better map. You still will have issues with contour compatibility and vertical separation. So usually what you'll have to do when you get the map out of the workstation is go in and hand edit the contours. So look for places like this where you don't have contour compatibility and see what you can do to add or make sure that you do have contour compatibility. But you'll notice that the reason we don't have contour compatibility here is the fault patterns are completely wrong. And they're completely wrong here because the interpreters did not make fault surface maps. They simply made fault picks and assign then the faults as their picks. And so the first thing I would recommend is not only pick and map your horizons, but pick and map the fault surfaces. And then you can integrate the horizon and the fault surface maps, and that will put everything much closer to where they actually belong before you grid and contour.
Thank you. It looks like the questions are winding down, so I'm going to give our listeners a couple more minutes to post their questions and remind you that you'll receive a link to the recording of today's webinar with an evaluation form and a link to registration details for Bob's class on QC techniques for reviewing prospects and acquisitions is offered in Houston, May 30th through June 1st. And it does look like we don't have any more questions, so thank you for attending today's webinar.
Yep, thank you, everybody. All right, no more dry holes.